Everything Chuck Moore has done is characterized by a dual stack architecture. He learned how to do this from Burroughs a long time ago. It was not a bad idea. The thing that is wonderful about it is that there is an independent data path for remembering where you came from and running loops, as opposed to remembering what the data are that you're operating upon. Other programming models have to deal with this problem, at least stack-oriented ones, by having stack frames, which are an enormous source of overhead and cumbersomeness in calling sequences, in management of the stack, and so forth. In the case of the fourth model, which is in fact the most visible aspect of fourth in these F18A computers, there are two stacks. There is a return stack and a data stack. There are registers associated with the top parts of both of these stacks. T and S are the top two elements of the data stack, conceptually, whereas R, a register, is the topmost element of the return stack. All of these structures are 18 bits wide. The data can move as the arrows show. The uses of the registers, T and S nominally are they are the two only inputs to the ALU. And at all times the ALU can be called upon to do an operation on T and S and replace T with the result. The R register is not only the return address, but it also can be the induction variable of a simple loop, an 18-bit wide induction variable, counting down, one direction only. This then forms the guts of the data movement model within an F18A machine. The other registers, A, B, P, I, are used for very specialized purposes, but for garden variety manipulation of data, this is the fundamental set of tools that we have available. We will now go into the actual operation of each one of these stacks in greater detail because they are implemented in a wonderful way.